Okay, let's go ahead and get started again. So I want to start back where we were before. We'd just gone through the chain rule for variance, which was our local to global theorem for proving variance contraction. And we applied this to the variance of DDIF to say it's the expectation over this local variance within the link plus sort of this global term that is some function on the underlying graph of the complex X. And I realized that maybe I should have started with the base case because this is an induction. It's an, yeah. Yes. Sorry. So this is analysis for the down operator that's on level. So D is the top dimension of the complex. I mean, you could do this analysis on any, I could have written K for any level on the complex because I can always just forget everything above K and it's still an HDX, so it doesn't matter. But D will just be the level that our walk is actually on, D to I to D. Just, I mean, the bound that you're going to get to, right? The bound from the hypercube for D to D minus 1 is 1 minus 1 over D. Right? It's dependent on the dimension. And so we're trying to match this bound of 1 minus 1 over D. So yeah. Okay. Right. So we'd applied this chain rule for variance. The base case, which is when I is equal to 1, is actually we're just analyzing this right-hand side. Right? Basically, the base case is just this local term doesn't exist. We're already mapping our function all the way down to vertices. And I'm going to make the following claim that is not particularly hard to prove. And maybe if we have time at the end, I'll prove it, taking inspiration from the previous, the pre-lunch talks. So I claim that you can bound the variance contraction of the D to 1 operator just in terms of dimension and the expansion of the underlying graph of the complex, which I wrote as lambda 2a, but remember that we have this bound of gamma 0 on this operator. So in particular, I claim for any generic complex that you can get this 1 over D plus D minus 1 over D times the the underlying graph expansion. And here we have a bound on gamma 0, and I've just rearranged, this is the same thing, but I've rearranged it to look like our, the way that we wrote the equation over there. So this is both the base case and like a key lemma, right? Because I'm also gonna use this to bound this second global term here. Okay, so what's our plan of attack? We want to bound this inner guy by induction, right? This is supposed to be on the link, and in particular, this should sort of be on the link on I sets. We've fixed one guy, so this is actually a walk to level I minus 1 instead of a walk to level I. And so we can use the inductive hypothesis to bound this inner variance term. So let me actually do that, because there is a slight trick, right? Because what do I actually have an inductive bound on? I have a bound on the variance contraction of the down operator of the link itself. But formally, as I've written this here, which is, what is this inner term? I have DDI of F, this whole thing restricted to V. This is what the chain rule, this is some function on the link of V, but it's not necessarily the down operator on the link complex V applied to F restricted to V. That's what we would have a bound on, right? Like we want something that looks like, I look at the down operator defined on the link of V itself, the local down operator from level D minus 1, right? It's a dimension of a complex of 1 lower dimension to I minus 1, so everything shifts down by 1, applied to F, this whole thing, applied to F restricted to V. So the parentheses are in the wrong place to apply this. Luckily, I claim that if you just write out exactly what this is, the down operator respects restriction. So these are exactly the same term. I mean, this is just the expectation. If I take this on some face T, this is just the expectation over the link of T union V, link of T union V of F. And if you write out this thing, it's also just exactly this local expectation. So I'll let you do it as an exercise, but both of these, whoops. If we had the diagram, both of these are still, you fix some guy from a lower level, and you average up over everything above here. It's just writing out the definitions to see they're the same thing. So really, we can rewrite this like we were hoping. we can rewrite this term as expectation I1 of the variance over the link of V of the actual local down operator d minus 1 to I minus 1 on V applied to F restricted to V plus this global variance term, which we know is bounded, but I'm not quite yet going to plug in our bound here. Okay, and now I can apply the inductive hypothesis, right? So I really don't want to write out that giant term that we get from the inductive hypothesis. So I'm just going to define. It should be. What should it be? Let me look at my notes. We're gonna set C to be equal to I over d minus 1 times the product of j equals 1 to I minus 1 of 1 minus gamma j. This is the term that comes from just plugging in the inductive hypothesis. Just trust me, you can look at it later if you want to. So technically 1 minus c is the term that appears. Now I wish I had created a little bit more room here. So now by the inductive hypothesis, this becomes 1 minus c times the expectation over pi 1, b sim pi 1 of the variance over pi v d minus 1 of f. Sorry, should this be I minus 1? This should be I minus 1. No, apologies. D minus 1 of f restricted to v, plus again this variance term. And now this is still local, but now I'm going to do the reverse step, right? I'm going to apply, just like I did in the trickling down theorem, I'm going to apply my local to global again to go the other way. This expectation of local is equivalent, using the chain rule, to what? This term is exactly the variance of f over pi d minus variance of d to 1 f. So let's bring back the 1 minus c plus the variance over pi 1 of d d1 f. And at this point, it's just calculation, right? Well, I mean, I'm going to plug in there's our key lemma here that moves variance of dd1 f to variance of f times this 1 minus 1 over d times 1 minus gamma 0. So I'm not going to do out the full calculation, but I'll write that this simplifies. So now I'm just going to group the variance dd1 f terms. By df plus c times the variance of dd1 f. And now we'll apply this claim, right? Now we'll bound this to get that this is less than or equal to 1 minus c variance f plus c times 1 minus 1 over d 1 minus gamma 0 of variance f. And I'm not convinced that it's all that helpful for you to see me do this calculation, that when I sum these two things, I get the right inductive term. So I'm going to let you do that on your own. Indeed, when you add 1 minus c and c times this, this is basically adding the gamma 0 term on. Remember that this inductive thing, what was this? This is like the product over all the 1 minus gamma j's, but I'm missing j equals 0, and my dimension is down by 1. If you go through the calculation, you can see that this will change this d minus 1 to d, and then this will add in the gamma 0 term that's supposed to be there. I'm not going to go through the calculation. Okay, that's actually the whole proof. If you do out the algebra as an exercise. But that's the main local to global idea going on. Okay, so one thing that I want to note, because I promised somebody that I would talk about it, is that this gets a spectral bound, which implies, for instance, quadratic mixing time of spanning trees. But we know that you should really get near linear mixing time for this type of object. And we'd like to prove that for matroids. Hopefully this thing will extend. So I won't go through this, but it turns out there are some stronger functional inequalities, something called log Sobolev equalities or modified log Sobolev equalities that have to do with entropy instead of variance. And if I were to try to use a similar method to bound these, I would bound what's called this modified log Sobolev constant of the chain, and I would get near linear mixing time. And what's the only thing that changes in this entire proof to do this? I replace the word variance with entropy. In particular, you can actually do this for any class of function or operator called phi entropy operators. I'm not going to go into it, but if you replace every occurrence of variance with entropy, the only thing that then needs to change is this base case. This base case is coming from the definition of local spectral expansion. Local spectral expansion does not promise you that the entropy of the d-to-1 operator contracts at all. So if you instead take as your sort of definition an entropic version of high-dimensional expansion, bounding this quantity, you will get hyperfast mixing bounds in the resulting complexes. And people call this entropic independence. There's a series of very nice works on it showing that log concave distributions, matroids, satisfy this type of entropy contraction. And people have been able to prove sort of hyperfast or near optimal mixing times of many, many random walks using this type of theory where we replace variance with entropy. But that's all I'm gonna say on that. I think the notes reference the name of the topic if you want to go read about it. Okay, I apologize. I'm not going to prove the key claim. If people want to know about it, they can talk to me afterwards. It's a very cute proof. It's in the notes also. You can read it. I want to move to agreement testing PCPs and how all this material is actually related at all to like local testability and what we've been discussing in the rest of this spring school. Before that, there's a little bit of a detour that will pay off, I promise. That has to do with concentration of measure. And we're going to see it connect back to exactly this bound that we've just proved, hopefully pretty quickly. Faster way to erase things. Okay, so I'm pretty sure that all of you know that a fundamental and extremely useful property of product spaces, and maybe in a less clear way that will become clear, the complete complex is concentration of measure, right? Things like Chernoff bounds, tail bounds, sub-Gaussian concentration. This is a core tool in theoretical computer science, pretty much regardless of your area. Pretty sure everybody has used the Chernoff bound at some point, right? This is a very fundamental and simple set of tools. And I want to talk a little bit about generalizing this or concentration on high-dimensional expanders. And then we're actually going to use that to prove some local testability type results, given I don't run out of time. Okay, so what in the world does it mean for a hypergraph to be concentrated? That is not an obvious thing. So let me propose a very simple definition and then argue that it sort of does generalize natural notions we consider in the literature. What does it mean for X to be concentrated? Okay, here's a natural definition. So let's say I have the vertices of my complex. I'm not drawing these in a square for any particular reason, just it's easier to draw. And let's say that some adversary comes along and they pick a function of the vertices. My first idea of concentration is that I'd like to show that if I sample a random hyperedge, that it sees the correct fraction of these marked vertices. Right? So an adversary comes along. Let's say they mark these bottom half of the vertices. We'll call this some set A. I would like to know in the complex X, if I sample a random D phase, say D is 4 here. If I sample a random hyperedge, is it true that with high probability, the density of A within this hyperedge is close to the global density of A? Right, so here A is half the vertices. So this would be a good hyperedge, right? Half of its guys are in A. It's what I expect. But if I picked, a horizontal hyperedge, I would completely miss A. And basically, I want to upper bound the probability that this happens, right? I want to say I'm going to call my complex concentrated if for any function A on the vertices with really high probability, I see almost exactly the right amount of A on the vertex level. And maybe people remember Swastik, definitely Dinur, maybe Swastik talking about samplers. This is really a sampling guarantee, okay? And I'll make this more explicit in a bit. But here's maybe how I'm going to refer to our question. What is the probability over sort of worst case set A that if I draw a face x1 through xd from my complex, that the number or fraction of guys in x1 through xd that land in A is close to its mean, is close to the measure of A. So this should be 1A xi, I equals 1 to d minus the measure of A, which in this case is just a half, but it could be something else. Is we want to upper bound this by some function of d, of dimension. So by, I don't know, some function of, sorry, this should say the probability that this is greater than, is off from the mean by more than some alpha, should be less than or equal to some beta that is a function of alpha and the dimension of the complex. Okay, this is a little abstract, so let's look at a particular example, the complete complex. Right, so let's change this to the probability that I sample x1 to xd from n choose d, right? Just the set of all possible hyperedges. And I ask, maybe I won't rewrite it, the same. What's the probability? And think of n as being really, really large. So really looking at this picture, think about this as I just sampled d, maybe there's like way more vertices, and I'm just sampling d completely independent vertices from this, because I have every possible hyperedge. So somebody tell me what is beta alpha d? What's the probability that my expectation is off by more than alpha if I pick d completely random vertices? Yeah, this is Chernoff, right? So this is Chernoff-Hofting. Without replacement, I guess, technically. It's negatively correlated, so Hofting, I think, proved that. But this should be something like, I'm going to ignore constants. It looks something like e to the minus alpha squared d, if you're not being all that careful. So then the question that comes up is, can we prove this on high-dimensional expanders, right? This is a property of the complete complex, or I could have done it over products in some slight other way. If high-dimensional expanders are indeed sparse models, act independent as variables, we might hope that they satisfy a Chernoff bound, right? That they give a de-randomized family, right? This has n to the d, roughly, possible hyperedges. A high-dimensional expander has only linearly many hyperedges. Is it possible that you nevertheless get this extremely strong concentration? Okay, so it's worth pausing to say, what do we know about this problem in general? What sorts of hypergraphs do we know satisfy a Chernoff bound? Or given the first couple lectures in the connection, the equivalence with distributions of bounded support, what sort of d-dimensional distributions satisfy, this would be called sub-Gaussian concentration? And the answer is that there's like an entire field of math that studies this problem. It's extremely well studied. It comes up in CS all the time because we have systems of variables that are weakly dependent, and you still want to prove some sort of concentration, right? An algorithm, graph algorithms, and things like this sort of thing comes up a lot. And there are a lot of general properties, like types of weak independence, that are known, which automatically allow your system to satisfy a Chernoff bound. With a couple exceptions, these are all properties that hold for very dense distributions. So these things typically are not going to work for these systems. There is one famous example of a complex that is very sparse and does satisfy this. And in fact, it's an example that Dinur gave in the second or first lecture. I don't remember. If instead of generating these from like an HDX or the complete complex, I generate them by taking a walk on an expander graph, right? A walk on a lambda expander. So this is drawn from sort of the set of walks on some lambda expander G. Then Dinur mentioned that you get some sort of bound like 1 minus lambda alpha squared d. Okay, by some constant. So we do have de-randomizations of like very sparse hypergraph systems satisfying Chernoff, which sort of begs the question, why do I care about concentration for HDX then? If we already have very sparse systems that I can use as samplers or that satisfy a Chernoff bound, why is somehow the notion of concentration on high-dimensional expanders more powerful? How has this helped us get local testability or PCPs where expanders seemed to fail beyond the 1/2 soundness barrier for PCPs? The reason is that a lot of these modern applications in hardness amplification need concentration for more general classes of functions. One way to think about this sort of bound is that A is like a linear function. It's a degree 1 function that sits on vertices of the complex. You might hope to say, have sampling for degree I functions. I might instead have a function that sits on level I of the complex. It's defined over I sets. And when I sample a D face and look over all of the I sets included in that D face, I might still hope that I sample close to the mean with extremely high probability. And there's a formal sense in which these are sort of degree I functions in the Fourier decomposition, but we're not going to get there. But you can hope to have sampling for broader classes of functions. So in particular, we'll care about these functions that sit on level I. So the question becomes the following: can you find sparse systems, or can we prove such a bound for HDX that for any set, or maybe any bounded function f sitting on the ith level of the complex, can we bound the probability again over a D face? I'll just write it as S is sampled from XD, that the expectation of T sitting of size I guys sitting in the D face S that we sample, the expectation of F. So this is our local expectation of F over the D face we sampled, minus the global expectation of F. Right, this was just the mu A over there. It's greater than alpha is less than or equal to, what? Can we prove some tail bound? Sometimes this is called like average case Chernoff and moving to level I. I think it's nice to think of it as sampling degree I functions, but what sort of sampling can we hope for in this regime? And maybe let me say, in the sampler graph view that was talked about before, this is exactly equivalent to proving that what? So this is looking at level D versus a function sitting on level I. So let's go back to this diagram that I erased, and I won't actually draw out the real version, but pretend I have all my D faces here, and I have xi down here. And exactly what I'm asking is a sampling question, right? I have some function, let's just say it's a set for simplicity. I have some adversarial set A of half the I sets. I'm asking what's the probability when I draw a D set that the fraction of neighbors going into A is close to the global average. This is exactly how we define sampler graphs, or this notion of sampling, in the first couple lectures, and we saw how powerful it was for building codes, AEL amplification, and stuff like this. Okay, so the question is now, like, we know hypergraph systems where if I have a function on x1, it samples it with the correct probability with Chernoff-like tails. Can I get a system that samples like this for every I? Okay, so again, the first thing to look at is the complete complex. Right? If we have all hyper edges, what's the correct concentration bound for this? Does anyone have a guess for this? Not quite. It turns out you have to pay in I, because there are correlations. It's not so obvious what the right answer to this is. So this was, as far as I know, if you look in the general probability literature, there are bounded independence tools you can use to apply to this. They don't get you quite the right bound. As far as I know, this was first explicitly studied by Impagliazzo, Cabinets, and Vigderson towards building combinatorial PCPs. And they proved the following bound, e to the minus alpha squared d over I. So you pay a whatever factor in the denominator of I. Why? Roughly speaking, I'm going to view my D set. I have like x1 through xd, and I'm going to divide it up into x1 through xi, and then xi plus 1 to x2i. I'm going to group it up into D over I groups, and I'm going to say each of these groups is independent. So now I'm basically just going to apply Chernoff on these D over I independent guys, and I'll get e to the minus alpha squared D over I. Okay, it shouldn't convince you that this is the right answer because it's just an upper bound, but it turns out that you can prove essentially a matching lower bound on this, and this is the correct answer for this sort of D versus I sampling. Okay, I also claim that we've already proved that high-dimensional expanders, okay, maybe not satisfy this bound, but satisfy some type of non-trivial concentration here. So can anyone tell me what the concentration bound we've already proved for this graph is? What should I replace here? So remember that what is this inclusion graph? What's the adjacency matrix operator of this? Well, the one directional is the DI, the two directional is the down up D to I walk. And what did we just prove? We proved a lambda 2 bound on this. And what did Madhur show in his first or second lecture? That this gives a Chebyshev style tail bound for sampling. So just using all the machinery we built in the last lecture, we are going to get, not this exponential bound, but we're going to get something like I over D, assuming strong, some reasonably strong local spectral expansion, like 1 over 2D or something like this. We're going to get a bound that's like I over D alpha squared. So if you think of D as being much larger than I and alpha as being a constant, this gets you some sort of non-trivial concentration here. Sorry, something I guess I should have said at the beginning is, what about expander walks? I didn't actually show you that those don't work for general I. So as an exercise, listed in the notes is an exercise saying that even for I equals 2, expander graphs are basically arbitrarily poor samplers for looking at pairs of edges that appear, or pairs of vertices that appear in an expander walk. It turns out you can construct functions sitting on the edges that are sampled extremely poorly. So we know that expander walks really strongly fail this type of behavior. And yet, for HDX, we're getting at least an inverse polynomial tail. We're getting some sort of non-trivial concentration. And to the best of my knowledge, these were the first, this is now over XD, these were the first bounded degree objects, the first very sparse systems that were known to satisfy this. This wasn't known before. There was a partial derandomization due to IKW using the Weizmann that was, instead of like size n to the d, it was size like n to the 5th or something like this. And actually this led to some nice PCPs of Dinur and Mayer. I'm not going to go too much into that. But we didn't have bounded degree or very sparse systems satisfying this type of constraint. So this is an immediate application, another beyond the amazing mixing theorems of this spectral gap theorem that we proved. And in fact, so one of those works that I mentioned leading up to that theorem, Dinur and Kaufman, this was actually their motivation. They didn't care at all, as far as I know, on the Markov chain or mixing stuff. The connection there hadn't really been discovered yet of the work of Inari, Lilova-Skran, and Vincent. They cared because constructing these objects implied what are called agreement tests, which are core components of PCP constructions, and was one of the core parts of that line of about 8 works that I wrote out towards getting PCPs. So my hope is to actually show you why this is useful in agreement testing in a bit. But first, I want to actually answer the question we asked. I have till 4:30, is that right? Okay, perfect. Yeah, we should be able to get through reasonable this. Okay, I'd still like to answer this question of concentration, right? Like high-dimensional expanders are supposed to be essentially the best possible sparse model of the complete hypergraph or of product spaces. You really hope that they do satisfy a sub-Gaussian or exponential tail. So what can we actually prove about this, or what is known? I'm not going to go through the proof. That would take another lecture. Though I'm happy to tell people how it's proved offline. And we'll use this version of the theorem in the agreement test, so it won't be useless. So theorem, Lichtenstein, Hopkins, or maybe. So let X be a one-sided let's say roughly 1 over 2d. You can get all the way to roughly 1 over dimension, but I'm just going to be a little informal here. Local spectral HDX. Unfortunately, we were not quite able to prove fully sub-Gaussian concentration. What is known for this weak setting is the probability for any function f xi to r, the degree I sampling probability. It's okay with people, I'm not going to rewrite this. This is just the probability that when you sample a D set, right, you're alpha close to your expectation. I wrote it out several times already. So I'll just rewrite, it's that exact thing. We prove something like e to the minus square root of alpha squared d over I. So this technically we would call exponential concentration, and this is some Gaussian concentration. And currently for HDX of around this 1 over poly D regime, it's open whether the correct answer is exponential concentration or sub-Gaussian concentration. I have no idea what the correct answer is. There are certain specific high-dimensional expanders, like the Ramanujan complexes, for which we know that they have sub-Gaussian concentration. But for a general bound just based on local spectral expansion, we don't know the answer. If X is a much, much stronger high-dimensional expander, so if X is something more like a 2 to the minus, like an exponentially strong high-dimensional expander instead of a 1 over sort of poly-strong HDX, this is either in the partite one-sided case or a two-sided case, then you can replace this with the correct bound, roughly e to the minus alpha squared d over I. So we know for very strong high-dimensional expanders, you do indeed essentially get bounds matching the complete complex or matching Chernoff. But I think it's a very nice question whether this holds for weak high-dimensional expanders. Okay. Yeah. No, we don't use Fourier analysis at all. The reason, yeah, I mean, there's a proof of this that we've figured out later that comes from a Poincaré inequality, where there's this like Poincaré implies exponential concentration, and it's known that Poincaré doesn't imply sub-Gaussian concentration. So there's some sort of barrier in like a Poincaré argument will never beat this, and you need some sort of HDX-based argument to beat to get here. The argument that actually we use here just directly looks at the moment generating function and bounds using swap walk expansion bounds that. But there's some term in the loss in the induction argument that is like lambda times something, and you get out some depending on how strong your thing is, you get some d to the 1 minus alpha and the exponent. We can talk about the barrier more offline. I think it's super interesting. But yeah, let's go to agreement testing so we actually see this connection with local testability. Yeah, Prahladh. Yeah. Mm-hmm. Yeah. Yes. Yes. Yeah. Do you want to know what the size of? Yeah. I can do that. Yeah. So the size of these guys, like the best. Yeah. The current, right? Of course. I mean, the size of this, the current best. Oh, actually, if I can cheat and use like really the best, like the Ramanujan complexes, then it's something like n times 2 to the d choose 2. So right, expander walks will get you like 2 to the theta d. In fact, even like the constant is very specific. The cost that we pay for having sampling even at edges is moving to d squared in the exponent. And when you try to use this to define codes and things like that, the rate ends up being terrible because of this 2 to the d squared. So it's a problem. We can talk more about it offline. No, this is like my favorite problem, and I have failed to solve it for a year. So I am pretty sure that the Ramanujan complexes should be degree optimal. That is my guess, and we can talk about it offline more, why I believe that. But there is no lower bound known. There are some lower bounds in my paper with Yotam that say if all of your links satisfy concentration, like satisfy Chernoff, then you have to have 2 to the d choose 2, or 2 to the d squared. But because we don't actually know that general HDX satisfy Chernoff, it turns out that while Chernoff gets you d squared, exponential concentration gets you nothing. Like it just gets back to the expander bound or something like this. So it's not known. Yeah. Okay. Ah. Yeah. Yeah. I'm not taking all I sets, right? You are giving me a specific. All I sets I bet you can do, at least for I equals 2. Let's talk about it offline though. Maybe you can massage Kaufman-Oppenheim or something to have a complete skeleton, and then that would allow you to. I mean, it's sort of cheating. That's just constructing an HDX that has the structure you want. I don't know is the answer. Let's take it offline. Yeah. Okay. Sorry. Let's go to the local testing. But I think there are a lot of super interesting questions here on the HDX side if people want to talk about it after. Okay, what does any of this have to do with codes, with PCPs, with local testability? So now I'm going to try to show you how to use exactly this, this guarantee of sampling between level D and level I on a simplicial complex to build what's called an agreement test, which is a core sort of combinatorial component in PCPs. I don't have that long, but let's see what we can do. We can probably sketch the idea. Oh, I guess. Okay, so what is agreement testing? This sort of is something that generalizes like the lines versus planes test. We actually sort of have talked about things related to agreement testing already in this school. I'm not going to go through exactly how they're connected, but we've seen related things to this. Like I think Reno talked about low degree tests. This is sort of supposed to combinatorially generalize low degree tests. We're specifically just going to look at agreement testing on a simplicial complex. You can define more general things, but you know we've been talking about hypergraphs and simplicial complexes the whole time, so we'll keep it at that. So on X. So here's the setup. You're going to be given a family of functions. Say this is d-dimensional. You're going to be given a family of functions on xd. We'll write it as script f. This is a family of functions, one indexed by each d face. And these functions are going to give a label, a 0, 1 label, to every vertex in this d set. So I'm going to have functions fs that map the set S itself, or the vertices in the set S, to 0, 1. You can generalize this to larger alphabets. It doesn't really matter. Let's just stick with 0, 1. And my goal is I would like to test whether this set, this collection of functions, maybe let me draw a picture. So say that this was D was 4, and this is one of my D sets, and I have these local assignments. You know, maybe this is 1, 1, 1, 0. I have some assignment on these 4 that's also 0, 1, 1, 0. I would basically like to test if these local assignments on these restrictions of the vertices given by the D faces of my complex are actually coming from a global function on the vertices. That really they're, you know, there's a reason that I had these overlap when I drew the same, you know, value on them. I'd like to test, is there really some global function, g, sitting on the vertices of x, such that the value of f of s is just equal to this global function g restricted to the set s. Do these really agree with some global function extension that's defined on the entire complex? Yeah. No, each s is being, somehow I'm confusing no, it's just 0, 1, right? Written like this. Each value of x I'm assigning a 0, 1 thing. I could write it as f. I could also write it as f2 to the s. Yeah. Okay. Thanks. Okay, so I'm only going to say this briefly. This is actually local testability of a code. What code am I trying to locally test here? It's what's called the direct product code. I don't want to go too much into this. I'm just saying it because we've been studying local testability. So let me briefly convince you this is really a local testability question. What am I going to try to do in this agreement test to solve this? I'm going to query a couple random d sets. I'm going to check if they agree on their intersection, and I'll say, I'll pass if they agree, and say if I see some disagreement, I'm going to say, okay, you're not actually a global function. I found some places where you're lying to me. So what is this? I guess we didn't technically do ABNNR encoding, right? We did AAL, but okay. So this is the following code. This is a local test for the following code called a direct product code. I have the vertices here. I have the d sets sitting up here. Every d set is connected to d vertices down here. And I take my code words are what? I take any possible 0, 1 labeling of the vertices. And I just concatenate the symbols that I see along my neighbors up here, right? So if this sees 1, 0, 0, 1, then this is basically getting the function, or the alphabet symbol you'll see looks like this. But we're just viewing it as a function from this d set to each position. So what am I testing? I'm exactly testing that I'm an element in this code, right? This is some subset of the space of total possible functions up here. And I'm trying to build a local tester that basically just checks a few of these guys that overlap in some of their positions and says, okay, you're probably a code word if they agree, and rejects otherwise. And the goal in agreement testing is to prove these same sort of notions of completeness and soundness that I think we defined for local testability, but let me write it back out. So sort of the goal, query a constant number of these d sets randomly, O of 1 s and xd randomly. And we'd like to have completeness, which means if you are truly a global function, right, if you're actually one of these code words, I should always accept. So complete, so if f is global, we want to accept. Maybe with probability 1, we'll actually maybe relax this slightly. And soundness, which is that if my test does pass with high probability, then I should indeed be close to being global. Right? So if my test passes, maybe with probability like 1 minus epsilon, I want this to imply that I'm sort of epsilon close to being a global function. What does epsilon close to being global mean? Maybe I should say like O of epsilon. This just means that the probability over a random fs guy that I draw, there is some global function g that I completely agree with, is like 1 minus epsilon. I only disagree on an O of epsilon fraction of stuff. So this is exactly a local test for this direct product code. And my hope is to actually prove to you an approximate version of soundness for this in the remaining 10 minutes using this sampling structure. Okay, any questions on the setup of agreement testing? Okay, good. So what's the test? Can somebody suggest for me a natural test on a high-dimensional expander, perhaps using the material that we've developed in the last several lectures? How should I pick? What am I going to do? I'm going to look at the two query case. I'm only going to make 2 queries. This is sort of important for PCP and hardness of approximation things. How should I design my queries for this agreement test? Well, 2 random ones probably won't intersect, right? So yeah, I should probably use the down-up walk, which is maybe what you meant. Because of this annoying, remember in this concentration thing, our bound was e to the minus d over I. We're going to think of alpha as constant, so roughly e to the minus d over I. So notice that if I pick 2 guys that intersected in half of their elements, which feels like it should be the natural test, my concentration is not so good. Yeah, in fact, there's really some constant here, so your concentration would be greater than 1, which is really bad. There is a way to fix this through what's called reverse hypercontractivity. I'm not going to go into it. It's quite complicated. So instead, I'll go down to level root d, where I have at least something like, for general HDX, e to the minus d to the 1/4. For strong HDX, e to the root d, or something like this. But I'll have exponentially strong concentration between levels d and root d. And I'm indeed going to take this suggested test, where I sample S, and then there's some intersection T, and then back up to sample S prime, right? This is the down-up walk. And I'm going to think of this now explicitly, instead of just S and S prime, I'm really going to care about this third guy T here. So I'm going to think about this walk as being over triples, STS prime that I generate, still just by the down and up operators. It's exactly the same process, just I'm like specifying this T now. And my test is going to be exactly what you think it will be. I'm just going to accept if f of s on T is equal to f of s prime on T. Okay, so clearly this is okay, actually I'm lying. Because I only have 8 minutes, I have to do the approximate version. So I'm actually going to accept if these guys are equal on all except an eta fraction of the domain. So I'm going to do sort of an approximate version of this local testability. And the guarantee I'm going to ask out is weaker. I'm only going to ask that the resulting function is sort of eta or O of eta close on all of the on most of the d sets to this global function G. Okay, so this is the approximate variant, which is a little bit easier to prove. And actually, the approximate variant is still quite important for things in hardness amplification. So we're not proving a useless theorem out of lack of time, just a slightly easier one. It's a workout to do this board. Okay. So let me write the rough theorem statement that we're going to prove. So I'll write the acceptance probability of this test as agreement eta of F. So this is the probability that the test passes under this eta approximate notion. So here's a theorem that's like adapted from Dixchain Hopkins based on sampling for, let's say, a 1/2D HDX, one-sided local spectral expander, for any epsilon that's greater than roughly e to the minus d to the 1/4. Think of eta as a constant for simplicity. If the agreement, if my test passes with probability at least 1 minus epsilon, then this implies that the probability over d faces that f of s is O of eta plus epsilon close to the majority function. Let me define what majority is in a second, but it's just the natural decoding on vertices. G majority restricted to S is greater than or equal to 1 minus O of epsilon. Okay, so we added some approximate things in, which is a little bit more complicated, but it's still roughly saying that if my test passes with high probability, then indeed, I can be assured that this is close to a code word in some sense. So it's some sort of slightly weakened local testability of direct product codes. Okay, I didn't define Gmag. This is just the natural thing that you would think, right? This is a function on the vertices where the value at V is I just look over all of the D sets that contain V and I take the majority vote of what, of their value. And so this is just the majority over the length of V. Or maybe I'll just say K sets containing V of Fs of V and break ties arbitrarily, doesn't matter. Okay, any questions about the statement before I give a sketch of the proof? Yeah, sorry, the test is going to be eta if they disagree on less than an eta fraction of their intersection T, then I'll pass my test. No, if I posed equality here, then I can get out equality as well, and it becomes much harder to prove. Oh, that would be only easier. Yeah. Yeah, so it actually turns out in application that having these, like testing for approximately being close to a code word, you need this in circuit average case hardness amplification and PCPs. So basically to make the theorem worth something, I'm adding this approximation in. Maybe I should have kept it out. But certainly, yeah. So actually I wanted to mention that if eta is equal to 0, and you use exact closeness over here, this is actually the original theorem of Dinur and Kaufman that was mentioned in both the spectral analysis and towards PCPs. They proved this exact 99% agreement test on HDX, which largely technically kickstarted a lot of these works. But so this is also proved through sampling and local to global method, but it's way more complicated. So I would need like two plus more hours to describe how that paper worked. This will be a very quick argument. I think I only have 5 minutes, so it better be very quick. Yeah. Okay. Yeah. Also perfect agreement with probability 1 minus O of epsilon. Very strong. Yeah. Yeah, it's a beautiful method, but it's substantially more complicated. Okay, so let me very quickly, I'm just going to give you the intuition for why sampling is useful here. I think theirs is majority. I mean, all these proofs are roughly the same idea, right? You use sampling to like make sure the majority is strong, and anyway, I'll show some version of it. Oh, is my mic off? No, I just turned down. Okay. So here's a claim that I'm not going to prove and is in the exercises. The first thing that I'm going to claim is that if I look at a random pair, so if I draw a random pair of a vertex and a d set from my complex, so this is distributed like pi 1, pi d, and this is from this joint distribution that we described. So I sample S and then V is a random vertex of S. So I want to argue, well, I'm not actually going to argue, I want to tell you that the probability over this pair, Vs, that Fs of V is equal to the majority value at V is, not equal to the majority value, is less than or equal to 2 epsilon plus eta. This is a technical lemma that uses expansion in the links. Expansion links is actually all you need to do this argument. It's a nice exercise in applying expansion bounds. But I'm going to take this for granted, that there's sort of this average case bound on agreeing with the majority that just comes directly from this agreement process. Basically, I localize the agreement over to agreement on links, and I apply expansion to get this bound. Okay, so I'm going to assume this and now show how sampling, given this fact, solves this problem. Okay, so I'm going to define two sets that live on XD. I'm going to define the sets of pretty good K sets and bad, D sets and bad D sets that don't agree with G majority. So we're going to have A, which is the D sets such that the probability that I agree with majority, that I disagree with majority, is less than or equal to 4 eta epsilon plus eta. So these guys are pretty good sets, right? They mostly agree with the majority. If I could prove that A was a 1 minus O of epsilon fraction of D sets, I would be done. It's not actually quite what we're going to do. Now I'm going to define a set B. And B is guys that I'll say strongly disagree with majority, but strongly isn't that much more. It's just like a constant factor more than this. So this will be the set of K sets, D sets, sorry, such that the fraction of guys in the D set that disagree with majority is greater than or equal to, say, 8 epsilon plus eta. Okay. So one thing that I want to notice, I have this average case bound on being less than or equal to 2 epsilon plus eta. So I claim that just applying Markov's inequality is going to tell you that A is pretty big. Not like 1 minus O of epsilon big, that's what we're trying to prove, but I claim that the size of A by Markov is at least a half. So it's a pretty big set. At least half the D sets are pretty close to G majority just by standard Markov. And I want to show that this implies that the probability of B is really small. It's actually at most O of epsilon. And if I can prove this, I'll be done, right? Because that says that all but a 1 minus O of epsilon fraction of D sets, less than 8 epsilon plus eta agree with the G majority function. Yeah, V and S are random over pi 1, pi d. Yeah, so this is okay, you should be a little careful and these are the same distribution that this is being defined over. That's why you can apply Markov to get this. But it's worth writing out to see it, just I don't have enough time. This is just Markov. Yes, it's very weak, right? Markov is just like, oh, this is going to be sampling. Yeah, this is not obvious. I'm about to tell you why this is true. This is very not obvious. I claim it follows directly from sampling. So here's the reason. I'll go over here and then we'll be done. But let me just explain why sampling is useful, because I built all this up. Let's now sort of change our view of how our test pair S and S prime, or the triple STS prime, is sampled. Right? Before we were thinking about it as first I sample S, I walk down to T, and then I walk back up to S prime. But instead, I could equivalently start by sampling T from root D, and then independently sample S and S prime. Okay, so now I want to draw the sets A and B up here. Okay. My goal is to prove B is really small. So I'm going to, for the sake of contradiction, assume that B is actually pretty large. Let's assume, towards contradiction, assume the probability of B is greater than, I don't know, 100 epsilon or 10 epsilon or something like this. Now the question is, what's okay, sorry. Why is this useful? Well, let me note that if S lands in B and S prime lands in A, then I claim that my test should reject with high probability. Why? Because sets in A mostly agree with majority, right? Many, the only guys that disagree with majority is some small 4 epsilon plus eta fraction. On B, there's a much larger subset of guys that disagree with majority, right? But how am I generating T? Marginally, T is sampled randomly from S and sampled subsampled randomly from S prime. So this means with extremely high probability by Chernoff that f of S is going to be close to majority on T. On the other hand, S prime, sorry, I did the wrong way. Let's say that S prime is in A and S is in B, then f of S is going to be far from majority, right? B is exactly the set of things that are far from majority. So when I subsample, Chernoff says I'm probably still going to be far from majority on this subset T. On the other hand, same thing here, I'm close to the G majority. So when I subsample, I'm probably still going to be close to G majority, but I can't agree between my two functions if this guy is close to G majority and this guy is far from G majority. And okay, I set up the exact constants in such a way that with really high probability, if I condition on passing between these sets B and A, my test will reject. So the thing that I actually want to argue towards contradiction is that if B is large, I'm going to pass between B and A with reasonable probability, greater than epsilon probability, and that will imply that my test rejects with greater than epsilon probability. But that my initial assumption was that I rejected with less than epsilon probability. So that would be a contradiction, and that would show that B is small. Okay, where does sampling come into the picture? I'm cheating a little bit because I have to flip some sampling guarantees to get this to work. But sampling says, with if I had sampling between level root D and D, sampling would say when I sample T, there's a good probability that I see the set A with the correct measure. Right? Sampling says that when I hit T, if A is of size 1/2, then probably about half of the neighbors of T up here are in A. So actually there's maybe a 99% probability that when I sample T and then I sample S prime, I'm going to have a 99% probability of sampling A well, and then I draw S prime independently from the neighborhood of T, and there's like a half probability I end up in A from sampling, right? On the other hand, this guy S is drawn independently as well. So if T also has many neighbors, I said this was size 100 epsilon. If this has 50 epsilon fraction of neighbors into T, if T has 50 epsilon fraction of neighbors into B, then the total probability that I sampled going between B and A is like the 0.99 probability that my sampling was good on this level times the 50 epsilon probability that I land in B here times the 1/2 probability that I land in A here, which is much, much bigger than epsilon. So the test will reject with probability much bigger than epsilon, and I get a contradiction, which proves the agreement test. I've cheated here enormously. Why? Because I didn't prove sampling to you from root D to functions on XD. I proved sampling to you for functions on root D from XD, right? I proved that if we had a function A sitting on this set, that I saw it with really high probability up here. It turns out you can flip sampling guarantees. That if you have a guarantee that says, for a 1% measure set down here, I see it with extremely high probability up here. It turns out you can prove that for, if I see this with e to the minus d to the 1/4 probability, it turns out that you can flip this guarantee and say that for 99% of the guys down here, I will sample well sets of measure about e to the minus d to the 1/4 up here. If I had more time, I'd go into more detail, but it turns out that you can flip back and forth sampling guarantees like this pretty much losslessly up to constants. So I've cheated in that I really only proved one of the directions of sampling for you. So I didn't explicitly show you that in fact 99% of the time I see A and B in the right proportion, but trust me that it's true. It's in the exercises to prove this. If you want to see really the formal argument done out, it's done in the notes also posted for the lecture. So I think I'm a little bit over time, but hopefully we got some idea of how sampling implies local testability or agreement testing. Okay, thanks.